Anyone joining for the first time today who did not join in the last class?
So this side Ruchit, my first class.
Okay. So we had a break for a week since last class. I'm sorry. Uh, I was not well and was had a lot of tasks on hand. So we'll do a quick recap of the last class's material and then we'll start with today's material. I guess people are still joining. Maybe we'll start with last class's recap and then meanwhile other people can join. Yeah. So in the last class, I introduced myself and given introduction to the course. Today's class will uh, start with the basics of EM theory. In last class, I reiterated quite a few times that electromagnetic theory is a prerequisite for this course. I hope there was ample time the last week for everyone to brush up their basics on EM theory. For everyone joining the first time, so in my slides, I kept this particular slide to include all the important information. So we're supposed to have classes on Monday, Wednesday, and Friday from 3 to 4:30. We'll try to do as many classes as possible. Sometimes I might skip a few classes, so I'll make sure that I put a message. And there has been some issue on the IEEE portal regarding upload of videos. So meanwhile, I'll be sharing the links to the videos and you can use them to rewatch the lecture, or if you are not able to join the classes on this particular scheduled time. There's a course website. I think I've not updated it, but yeah, so only one classes and all the material I'm also sharing on the WhatsApp group. Here is the meeting link. So if you have the slide, you can always use the slide to get the URL. Also, the meeting link is there in the WhatsApp group's description. So I also gave an assignment last week. I hope everybody was able to at least take a look at it. So we'll discuss the assignment. Need not worry. So you'll have more time to because some of the questions were asked in advance. So we'll cover some today. We'll cover some in the next class. So these are the references which we are following. So I'm making my lectures from Podzar, and there were some questions from Cheng. So because we are doing basic electromagnetics right now. So the last class we covered introduction to microwave engineering. We'll cover module 2 this in today's class and coming few classes. So we looked at the introduction to microwave engineering, how it started, and some applications. And the last class we covered the electrostatic and magnetostatic fields, time varying fields, and briefly talked about the Maxwell's equations. So we'll do a quick recap. So just looking at the slides, you might recall because there has been a lot of gaps in the last lecture. So we looked at the frequencies which correspond to microwave and RF, and why do we call millimeter waves as millimeter waves. So this chart is there, which will help you determine in which frequency range you are working and what do you call that particular frequency range. Similarly over here, the L band, S band. So all these are the terms which are used by people working in RF and microwave engineering, and to classify in what applications they are aiming for. For example, somebody might tell you this is an S band radar. So yeah, so then you'll know that that particular radar works in this particular frequency band 2 to 4 GHz. Similarly, if somebody asks you to design a X-band filter, then this is a cue to you that you have to design a filter, band pass filter from 8 to 12 gigahertz. Yeah, so this is all the nomenclature used uh, in RF and microwave engineering. We also looked at why the field of microwave engineering is necessary and what brought about it. Because for, at, for normal KVL, KCL, these circuits assume that there is no phase change when the voltage and current or the wave is when they're propagating through it. But at higher frequencies, the wavelengths become shorter, and there might be a phase change when inside the particular element. So for that, you need to study microwave engineering so that because KVL and KCL won't follow in that cases because you will be dealing with phase as well. And similarly, even higher frequencies, you can assume them to be as rays, and the field of optical engineering, they use geometrical optics to solve the problems. So I asked everyone to look up the differences between loved and distributed elements. That will help you know better why microwave engineering is necessary, because will be dealing with distributed elements. Some of the applications we looked at, for example, very popular antenna engineering, radar systems, wireless security, satellite communications. Right now, very popular IoT systems, again, environmental applications, industrial applications. So yeah, a lot many applications, a lot many different areas to work when you're working at microwave engineering. We looked at the history of microwave engineering, how it started. Right now, what we know as the electromagnetic engineering is essentially started with J.C. Maxwell. So there we have the pictures over here, very handsome men doing extremely good work. Did extremely good work. And Oliver Heaviside then compressed the so many Maxwell's equation by introducing vector notation to just 4 equations that we right now know as Maxwell's Heaviside equations. So it all started with Hertz when he designed the first apparatus for the electromagnetic experiment. Here is the setup. You can find this picture in Podzar. Uh, and so all these things have been labeled, and you can go through them to see what particular element is uh, used for which particular thing. So very interesting. You can see these two balls over here. They're connected by this particular wire, and this is essentially the dipole which we know now. So yeah, so we discussed this, and then we started with the electromagnetic theory, where we looked at the divergence and Stokes theorem. So very popular, been taught in basic EM theory. So uh, it's an interesting fact that Stokes theorem was actually given by Lord Kelvin, and although we know it as Stokes theorem, and then this is Gauss over here, and like that when the electric charges are at rest, we have the electrostatic fields. When uh, we then the magnetic charges, which like for example, when there is a magnet, we have these magnetostatic fields. When that is or when we have an electric charges moving at constant velocity, and if they are moving at with acceleration, or we have time varying currents, then we have uh, the electromagnetic okay, electromagnetic waves. So yeah, so we looked at the electrostatic fields, the differential form of the Gauss law, the conservative field. So this is all there in your textbooks, basically in theory. I hope everybody has it revised. So I asked a question: why do we stress on this Laplace equation? And similarly, why do we stress that this particular is of the form Poisson's equation? So anyone wants to answer to this question? Why do we stress that this is a Laplace equation, this is a Poisson's equation? Okay, so essentially we stress on this because these particular form of equations have a known set of solutions. So if you're solving a particular question, and if you are able to make it look like either of the form of Poisson's equation or Laplace equations, you can easily refer to a standard textbook or a paper which will give you how to solve any equation which becomes of this particular form or this particular form. So all your work will be to derive your particular problem so that the you get this particular equation, and once you have this equation, you can easily look up reference material and write the solution right away. So that is why like these are stressed a lot, that this is a Poisson equation, this is Laplace equation. Similarly, we studied the magnetostatic fields, looked at the notations, the Ampere's law, the Gauss's law for magnetostatics. Then again, we looked at the auxiliary potentials and yeah. Um, so we started with the Maxwell's equation in the last class. So we'll discuss more about it today. So this is James Clerk Maxwell, and here are the popular Maxwell's equation over here. So we have the divergence and curl of electric field and magnetic field, and electric flux and magnetic flux. So essentially, when we so this electric flux and the magnetic flux can be expressed uh, can be expressed in terms of like electric field and magnetic field, and hence it can be also written as del dot E is equals to rho by epsilon of that form. And if we know the curl and divergence of a vector, we can actually fully describe it. So yeah, so over here is the list of notations and their particular units. So this is very standard. You must know this. Yeah. So we have the differential form, the integral form, and the constitutive relations, which uh, fill the missing gaps from the differential equations. Yeah, so we'll start here today. So any arbitrary time-dependent field of the form F, which is which is dependent upon x, y, z, the three space coordinates and time, or we can write the space coordinates as r. It can be expressed as a real part of F. This is the scalar part, and this is the magnitude part, and then this is the phase part, e power j omega t. So when you represent in this form, it is known as a phasor, and this is as then the RE is actually taking the real part of the quantity inside the brackets. So yeah, so this is the phasor form. So and this actually contains the information in terms of phase. So for any vector quantity varying like sinusoidally, so it will have this omega component over here, and you can actually write it in this form, and this makes our life a lot simpler. You just you can the addition, multiplication, and all operations become way simpler when you're using the phasor notation. So the EM field quantities, for example, the electric field, electric flux, magnetic field, and the magnetic flux, they can be written as in terms of phasors. And from now on, we'll mostly use the phasors to solve and look at our equations. So we already saw this. Yeah. So once you have presented them in terms of phasors, and you know if if the derivative of e power j omega t will turn out to be j omega e power j omega t. So you can easily replace the derivatives terms using this in the Maxwell's equation. And this is the another form of Maxwell's equation. I hope everybody is familiar with this. So where the derivative terms are gone, and we just have j omega in place of the derivative terms. So makes it lot simple. And so essentially all the derivatives are gone, and all you need to do while solving this is uh, club them into imaginary parts and solve the problem. Now, another important topic in EM theory is the fields inside the media and boundary and at the boundaries. So for any dielectric material, an applied electric field causes polarization of the atoms or molecules. So in presence of fields, we use a pen over here. So for example, if there is an atom and there are electrons outside, something like this. So if there is electric field like this, you will notice that the electrons tends towards the higher potential part, and the atom will the positive part will move towards the lower potential. So something like this. So this will actually get polarized, and if you effectively see, you will see that any neutral thing becomes polarized of this particular form. So essentially, what we call this is polarization. That is, the poles are coming apart. So this particular polarization can be expressed in terms of this vector, and which we call as the electric polarization. So PE is the electric polarization, and we can represent the total displacement flux in terms of the electric field applied to it and the polarization uh, of the media of the dielectric material. Now, the polarization itself can be expressed with respect to the applied electric field, and it is given expressed like so. This is the permittivity of free space. This is chi e, which is the electric susceptibility, and this is the electric field. Now, if you substitute this back over here, you can express it in this form where 1 plus chi e and epsilon naught together can be written as the permittivity of the media. So I hope everybody is already familiar with this. So I'm going a little fast over here. Uh, Maybe we'll stop somewhere and take questions. So chi e is the electric susceptibility, and you can express the electric flux in terms of electric field directly relating it to the electric permittivity of the free space. Uh, so if this epsilon can be expressed in terms of real and imaginary part, which is equals to the epsilon naught times 1 plus chi e, and we call this as the complex permittivity of the medium. So over here, all lossless media have this as a real, and there is no imaginary part. And if the media is lossy, we will have this particular imaginary part. So this imaginary part actually like shows the loss, which is again due to the polarization of the media. And if the polarization of the media, like if there is a delay, like for example, if you apply an electric field and there is polarization, and then you change the polar. For example, if you are applying electric field in this direction over the media, so it will become like this. So, but again, if you change the polarization direction, you will see that it will have to come to uh, the field will have to change its polarization like this. But there might be some delay when you are switching between these two states. So this delay is actually the loss. So there is some resistance offered by the dipoles in changing the positions. So that is expressed as this particular loss and by the imaginary term. So the imaginary part accounts for the loss in the medium, and this might also result into heat, which is uh, due to the damping vibration of the dipoles. Yeah, again, so as I explained, so if there is a slight delay when you apply the field to the material, so there might be some delay, and it might lead to the dissipation in form of heat and vibration of the dipole. So this particular part will express the loss of the media. Uh, okay, so free space has only real part of the permittivity, and hence it is lossless. In any material with conductivity with express as sigma, will have a conduction current, will can express the conduction current. So where this J is the conduction current density, and it can be expressed as J equals to sigma E, which is the which we already saw. This is known as the Ohm's law. So the Maxwell's equations can be then expressed uh, like this. So this is the Maxwell's equation, and we can replace the J by sigma E, and again the sigma E. Uh, so we have E over here, E over here. So taking and the sigma E can be expressed in terms of okay. So I think we lost. something. Anyways, yeah. So we can express the sigma in terms of omega epsilon plus j sigma. Okay. Yeah. So the sigma e, and then we can take the imaginary part. Is something missing? Just give me a second. Yeah. So once substituting the epsilon over here as epsilon dash j epsilon double dash. So we substitute that over here. We take this imaginary part at one place and we take the real part over here. And then again we take the imaginary part as common. So we end up with this particular expression over here. So this is actually we can write the entire thing as epsilon. Yeah. So this particular part can again is together giving the relationship between the ma magnetic field and the electric field, and this that over here, which if we take the if we just look at the imaginary part over here, we can define a term called the loss tangent, which takes into account the loss part. So if you take the j common over here, so you will get omega times epsilon double dash plus the sigma over here, and in the denominator, if you just take the real part outside, so you'll have the denominator epsilon dash over here. So yeah, so this is what we define as loss tangent, and most people working in antennas and microwave will sometimes define the material property in terms of the permittivity, which reflects the real part actually, and again as the loss tangent. So if you have the real part of the permittivity, the dielectric constant, and then also know the loss tangent over here, then you can easily uh, find out the, the imaginary part of the media, imaginary part of the permittivity. Okay, so we'll stop probably here and take questions if you were not able to follow, maybe I can repeat. Yeah, any questions so far? You can let me know if I went too quickly. I can repeat the last few slides. Okay, so I guess this is fine. Everybody was able to look at the basics last week. Again, so we already saw this in the last slide last slide, that we can express the electric flux in terms of the electric field uh, by the permittivity of the media, which can be expressed as a permittivity of free space multiplied by 1 plus chi e. Chi is the electric susceptibility. But over here, what we assumed was that this polarization vector and the electric field were in the same direction, which essentially means that we had this relation P is equals to chi e epsilon naught chi e. So, and we assume that these are scalar. But what if they are not scalar, which is usually true for many media? In that case, we'll have to represent it differently. And so if this particular relationship holds true, we call those media as isotropic materials, because uh, the polarization is in the same direction of electric field. But for medias which do not follow this relationship, where this relationship is not linear, we call them as anisotropic. And so the most general relationship between these two vectors when they are not linear, so takes of the but requires the use of tensor. So you can represent the electric flux and electric field using this particular equation, where for each the permittivity is expressed using this particular tensor. The tensor is actually a matrix which is used to give relationship between two vector quantities. So it itself is a scalar quantity, but this matrix is what we call tensor. So need not worry if you are hearing this for the first time. So we just this matrix we are calling it as tensor. So if this particular matrix if they so if these particular values are different, then the material is anisotropic. And for isotropic materials, this particular matrix reduces to something of this particular form. So you have the simple linear algebra, if you recall, you can actually represent this as a scalar quantity multiplied by the identity matrix. So that is what is true when you are considering the media to be isotope. Similarly, for magnetic materials, we can express the magnetic flux density in terms of the magnetic field and the magnetic polarization represented by PM. Okay, so one thing to notice, I'm using this notation over here where well, if something is written in bold, it means a vector, but in the equations we have this particular bar over here, so and which this also means vector. So need not be confused like what this particular bar is over here. This particular bar actually means this particular quantity is a vector, and in text I'm using bold for it. So we have this particular equation, and for linear magnetic material again we can express it in this form, where chi m is the complex magnetic susceptibility, and substituting this equation back over here, we have this particular we can express magnetic flux in terms of the magnetic field, where this mu can be expressed by this form, and it can be again written in form of a plus gb, which is the real part and the imaginary part separately. And again over here also this particular term represents the loss. And this is called the complex permeability of the medium. So this follows exactly same as the what we did for the electric field and electric flux. And again, for an anisotropic medium, we can express the magnetic flux in terms of the magnetic field by using this tensor for magnetic permeability, and this the magnetic permeability of the medium. Now, for a linear media, that is when we have these as scalars, and they do not depend on electric field and magnetic field. We can simply write the Maxwell's equations in this form, which we already have been doing so far. So I'll stop over here again. So let you absorb what all has been discussed till now, and take any questions that you might have till now. Okay, I guess no questions. Again, so yeah, so we have the constitutive relations also for this equations where these two quantities may be complex or tensors. Now, coming to the boundary conditions. So while solving the Maxwell's equations, we looked at how we do it inside the media, but what happens at the interface. So taking a general material interface where the medium one is specified by epsilon one and mu one, and medium two is specified by epsilon two and mu two. So the electric and magnetic field in the both regions can be defined as H E the E1 D1 H1 and B1, similarly B2 H2 E2 and T2. So while solving at the boundaries, we'll consider the magnetic flux density in the normal direction, and we'll consider the magnetic field in the tangential direction. Hence this notation T and N over here. Similarly, we'll look at the electric fields in the tangential direction and the electric flux in the normal direction. Solving for either of them will give us sufficient information for the electric field, and so solving for them will give the information for the electric field at the boundary, and solving for these will give us the information for the magnetic field at the boundaries. So we have Js and Ms, which are the electric current density and magnetic current density. This is fictitious while solving the Maxwell's equations. And we have rho s, which is the charge density on the surface. So we'll solve for all these four cases one by one. So taking a so solving for the electric flux density at the interface. So we use this very standard technique known as the pillbox. So we consider this pillbox at the boundary. So this is a very small volume on the interface, and so we have the electric flux normal to this particular surface, and there will be flux in these direct way here as well. So if we diminish this edge, so this if this edge reduces, so this will actually result in a very thin volume at the just the interface. So as the limit h tends to zero, the contribution of the tangential through the side walls goes zero. So essentially, this is saying that we have uh, the electric flux coming outside these walls as well. So which we are calling as d tangential. So if this h becomes zero, this d tangential contribution will tends towards zero. So then, taking solving this particular integral, we can just write this. So this area is delta s. Similarly, the area over here, this will be also be delta s. So the flux on this particular surface and flux on this surface, and their difference is equals to the charge on the surface, the charge density multiplied by the area of this particular surface. So you can write and then solving it further, so we can cancel out the area term, so where we get the electric flux. The difference of the electric flux is equals to the electric charge on the surface, charge density on the surface. And we can express this in terms of vectors, where so this normal component multiplied by the uh, electric flux is equals to the charge density. And if we do a similar formulation for the magnetic flux, will get this particular relationship. So this essentially means that n times this b2 minus b1 equals 0. And this is so essentially we are saying that there is no particular the rho for magnetic charges, because we know that magnetic monopoles do not exist. So this particular thing will come out to be zero. Similarly, solving for the tangential fields, so we have this particular Maxwell's equations integral form, and so for this, we are taking right now, we're taking a surface integral. So this essentially this overrides on the left hand side we have this line integral, and override in the right hand side we have the surface integral. So if this particular h again tends towards zero, so what we'll have is the contribution of the this magnetic flux will become zero, because this particular area this area will reduce towards zero. But and for the mag if we have this magnetic current on the surface, uh, this will contribute towards the electric field over here. So the contribution of the surface integral of m may not be maybe non-zero, because if we're considering that the surface current density ms exists on the surface. So again, so this particular relationship will turn out to be like this: delta L times E tangential. So this is delta L, and then we have E tangential in this direction, and we have again E tangential on this direction. So that difference will be equal to the magnetic current, surface current, into the length of the this particular side, and then canceling out this length terms, we have this relation. So this gives the boundary condition for the tangential electric fields. We can again express this in terms of vector. Right now, this time we'll take a cross product, and we have the known form of the boundary condition for electric field at the general material interface. If we do a similar formulation for tangential component of the magnetic fields, we'll end up with this particular equation. So this is also known to us. So in this case, we'll, instead of having a magnetic surface current, we have the electric surface current. So I'll encourage you to do derivation for this by yourself, and similarly for the normal magnetic flux, a normal component of the magnetic flux in the previous slide. So we'll stop again over here to take any questions if you have from the last three slides. I hope I have not lost you guys. Can anybody just confirm if I'm audible? That will let me know that I'm still.
Yes, I know.
Okay, so I guess then everybody is either following it very nicely, or you're not following it at all. I hope it is the first case. Even if you, since this is all what has already been taught to you in electromagnetic theory, I don't think this should be a problem. But if you are losing me on this on these slides, need not worry. I think there is enough information written on the slide itself. You can read the slide, or just refer to the textbook. DK Chang, I think Sadiku is very popular as well, or Podzar itself. I've prepared the slides from there. You can go through them. This is all the big in the beginning of the first chapter of Podzar. That should not be a lot of trouble for you guys. This is all this is important before we start with the transmission lines. So yeah, so right now we have discussed the Maxwell's equations in the time harmonic form, and now we are looking at we looked at the fields inside the media, the polarization and relationship between the constitutive relations, and now we are looking at the boundary conditions. So we have discussed the normal and tangential components of the boundary conditions. So finally, all the discussions can help us determine the boundary conditions in these three popular cases. For example, if for the so the first popular case is fields at the dielectric interface. For example, if you are moving from one dielectric to the other, over there you'll use the first set of this particular set of boundary conditions. But if one of the one of the media is an electric conductor, which PEC is perfect electric conductor, then you will use this particular set of boundary conditions. So over here you see that one of the interface is so. In case of PEC, what happens is there is no field inside the PEC, and we only have charges on the surface. The first equation changes to this case, and yeah, so we don't have any magnetic flux and electric flux, and we again the normal component in one of and the dielectric will be given can be calculated from the surface current on the material on the PC. Similarly, we can give relationships for the magnetic conductors. So magnetic conductors do not exist, but knowing these boundary conditions are very helpful in solving a lot of problems where we use where we use duality property, which you'll see in coming lectures. So, but knowing this is very good. So one of the popular use of magnetic conductors, which we think of, is when we are designing antennas, and we sometimes use a surface below the antenna, and we call that as a magnetic conductor. So yeah, so we have some applications where we try to design magnetic conductors, and where these particular equations come in handy. So we'll start with wave equations now. Maybe I'll again stop over here, give you some time to think about all the things that we have done till now, and then we'll start with the wave equations. So we'll look at wave equations and waves in lossless media today, and then we'll close for today. We'll also discuss the assignment that we had last week. If you have any questions regarding that, and then we'll close. Arachit, you were joining us for the first time today, right? Yeah, I guess not audible. Yeah, anyways, need not worry. You can refer to the last class's lecture and today's. So someone in the last class asked for a change of time for the class. So, I looked at my schedule, and I don't think it will be possible for me to shift the dates or the timing. And also, I've already announced it. So maybe we might have to or cancel a few classes, but for that we might put some extra classes on the weekends. So, or we can have additional classes to discuss doubts or assignments on the weekends. So if you're not able to attend the classes in the regular timing, we can do that. But we probably won't be able to change the class timings. Okay, so we'll start with the wave equations now. So the wave equations are given by the this particular two sets of equations. So as an assignment, I will leave the derivation of the wave equations from the Maxwell's equations to you. So you just have to use this particular vector identity on the two Maxwell's equations which have the curl of electric field and magnetic field in them, and do a few steps and you will get the answer. You can also refer to Podzar. It has a derivation. So yeah, so the time-dependent vector Helmholtz equation, um, or the wave equations for a linear isotropic and homogeneous medium, and that too for the source-free medium, is given by these two equations. So what we mean by linear isotropic and homogeneous so essentially we are saying that uh, the uh, the polarization vector and the electric field are in the same direction, and the permittivity is same for in all directions, and homogeneous means that the all the points in the space in a particular media have the same permittivity. So I'll ask everyone to look into these three terms, very important. Uh, Maybe I can discuss them in the next class, or rather this could be a good question for the assignment, and then we can discuss. Yeah, so the Helmholtz equation or the wave equations are is given over here, and for this particular wave, we define its velocity by as given over here. So where mu and epsilon are the permittivity and permeability of the media, and we define what we know as the propagation constant, or the wave number, as k, which is equal to omega times root under epsilon mu, where omega is the angular velocity of the wave. So looking at the plane waves in lossless medium. So in lossless mediums, as we discussed, the permittivity and permeability are real numbers. That is, we do not have any imaginary part to both epsilon and mu, and hence the k is also real. So we have defined k equals omega root under mu epsilon. So if both epsilon and mu are real, the k will also be real. Uh, so for looking at a solution for a wave equation for a very simple case where we only have electric field in the x direction, and we only have the x component and there is no variation. You know, sorry, so there must be some error. We do not have any variation of electric field in the um, z or y direction. So okay, so there is no variation in the x or y direction. So we'll have uh, the partial derivatives in the x and y direction as zero. So we'll have the Helmholtz equation will just end up something like this. So we only have the electric field in the x direction, and there is no variation in x and y direction. So that is the E field. This Ex is only varying in the z direction. So we will have the Helmholtz equation reduced to this particular form. And for this particular differential equation, the solution can be given by this form, where you can easily check if this is valid or not by substituting the solution in this differential equation, and you'll see that this thing satisfies. So over here, the E plus and E minus are the real quantities, and this and the minus the term representing having this minus jkz is essentially talking about the forward propagation, and the positive part, the positive a power j minus a power jkz is looking at the negative towards the negative direction. So for the solution, we have this E plus and E minus. These are arbitrary amplitude constants. So essentially, we're just looking at the general solution to this particular differential equation. And again, you can write this particular equation in time domain as well. So this is the phasor form, and in the time domain, we can write this as E plus cos omega t minus kz and E minus cos omega t plus kz. So we started with the Helmholtz equation, and for one particular case, we have the differential equation of this form, and its solution is given by in phasor and time domain by these two equations. Now we can define the phase velocity of the wave as the velocity of a fixed point velocity. It is the velocity at which a fixed point on the wave which with fixed phase point on the wave. So essentially, if you take a wave which is propagating, so if you take this particular point on this wave, and if you check the velocity for this particular point, so that particular velocity is known as the phase velocity. So we can define, we can take a particular so the wave velocity, we can define the wave velocity as dz by dt, and z can again we have, so for this particular is equals to constant, we can find out z, and it will be given by omega t minus constant by k, and taking the derivative we will end up with omega by k, and this but substituting k as omega by omega root under mu epsilon, so you'll end up with 1 by root under mu epsilon. Now a question to you, can you calculate the phase velocity of a wave traveling in free space? I hope you guys have a calculator on hand. So all you need to do is substitute the value for mu and epsilon for free space. For free space, this mu will be given as mu naught and mu r. So mu r is 1 for free space. Similarly, epsilon is given by epsilon naught epsilon r, and again epsilon r is also 1 for free space. So you need to multiply mu naught and epsilon naught and take 1 over root of that particular value, and you will get the phase velocity for a wave traveling in free space. So yeah, so taking the root of the mu naught and epsilon naught, what we get is, we also know it as c, which is the velocity of light in vacuum, which is 2.998 into 10 power 8 meter per second. Another quantity we call this as wavelength is the distance between two successive maxima or minima. So if we have, let's extend this. So the distance between these two maximas, or let's have again have a minima over here. So distance between these two minimas is known as a wavelength. So introducing this term wavelength lambda by presenting as lambda, and if we take this difference equals to 2 pi, we can calculate the wavelength as lambda equals 2 pi by k, and again substituting the value for k as from above, like we saw that omega by k equals vp, so we can substitute that, and we get lambda equals to vp by f, where f is the frequency in hertz. Yeah. So a complete specification for the plane wave in electromagnetic field should also include the magnetic field. And if you know the if since we have the Maxwell's equation, and if you know the electric field, you can find out the magnetic field from the electric field, or if you have the magnetic field, you can find out the electric field from the magnetic field. So if either of them is known, the other can be readily found out by using one of the Maxwell's curls equation. So if you know the electric field, you can just take its curl and get the magnetic field. And if you know the magnetic field, you can just take its curl and find the electric field. Uh, yeah. So applying curl. We already had the solution. So and then applying curl to this particular electric field, we get that hx and hz are equals to 0. So I'll recommend you perform the curl actually on this, and find out for yourself, so like whether you get hx and hz as 0 and hy equals this particular equation, and then you'll end up with this particular derivative and finally this particular equation. So you will get this. I'll let us try over here, so that doing some hand calculations will help uh, revise the basics. So over here we have defined this particular term as eta, where eta is omega mu by k. Uh, so we have replaced this term by eta, and this is also equal to mu by epsilon. If you just substitute the value of k over here as omega root. Just a second. So if you so if you just substitute the value of k over here, you will see that this intrinsic this eta is equals to root under mu by epsilon, and we call this as intrinsic impedance of this particular medium. So this is another quantity which specifies the media. So another quick question to you: can you calculate the intrinsic impedance of free space? Again, all you need, we already know that eta is equals to root under mu by epsilon, and for free space, this mu will become mu naught, and epsilon will become epsilon naught. So all you need to do is substitute the value of mu naught and epsilon naught, and you will get and just take the root. You will get the value of intrinsic impedance for the free space. So this turns out to be 377 ohm. This particular value will come in handy in a lot of places. This is I think also equal to 120 pi ohms. So this will come in handy in a lot of calculations in coming lectures. So let's do a quick example. Okay, before that, maybe we'll pause over here and take questions if you have any from what we have discussed till now. Sorry about that. Yeah, I have not been well for past few weeks. So sorry about that. So yeah, so taking any questions we have till now or from the previous class or whatever we have discussed. So we'll just have one more example to look at, and then discussion of the assignment, and then we'll close for today. Maybe I can make a poll to ask if we have looked at the assignment or not. Yeah, so I think I've launched a poll as well. Maybe I'll get some chance. Maybe you can respond to the poll and I'll get an idea whether you received the assignment or not. So I guess no questions so far. I'll give you time so that you can respond to poll as well. Yeah, so I can see 4 responses. Well, I think quite a few people are away. No worries. The assignments are just meant for you to keep track of your progress in the class. And anyways, the assignment was sent in advance. You have some classes to look at them. Just in case you missed or you were added late to the WhatsApp group and you're not you're, you're not assigned as a student on ISSS, maybe you can put an email to me. Uh, I'll write my email for here as well. So yeah, this is my email. You can put an email to me if you are not added as a student on ISSS, if you have not received the credentials, missed the assignment. Again put it up in the WhatsApp group today. Maybe I'll put another assignment in coming maybe after the next class. Okay, so we looked at the wave equations and for a plane wave in lossless medium. We'll do lossy medium in the next class. So for today, we'll just solve one question, very simple question. This is an example in Podzar. So, so we have a plane wave propagating in a lossless dielectric medium. So we know that uh, as it says lossless dielectric medium, we know that the epsilon if we write it as the form epsilon dash minus j epsilon double dash, as soon as we read this is a lossless medium, we know that this particular term is equal to 0. As an electric field given as Ex equals to epsilon E naught cos omega t minus beta z with a frequency 5 gigahertz. Okay, so we have the frequency with us. So we have uh, f, and the wavelength of the material is 3 centimeters. So we also have lambda. So we need to determine the propagation constant, the phase velocity, the relative permittivity of the medium, and the wave impedance. Okay, so maybe I'll just discuss the answers with you. So for the propagation constant, we have propagation constant k. Uh, we can express it as 2 pi by lambda, and substituting the value for lambda. Note that this was given in centimeter, so we first convert it to meters, and then use calculator over here, and just put the values inside the calculator, and you will get this particular answer. So it is 209.4 per meter. So we have the propagation constant now. Let's calculate the phase velocity. The phase velocity is given by omega by k. We already have f. So from f, we can calculate omega by 2 pi f. And we already calculated k over here, substituting the value of k. You can either do this, or you can just replace 2 pi by k by lambda. So so we already had this particular value. So 0.3 the centimeter, just converted from centimeter to meter. We have 5 gigahertz. So gigahertz, that means 10 power 9. Multiply them and you have your phase velocity. Now calculation of relative permittivity of the medium. So we already have expressed this. Okay, so relative permittivity. So for Vp can be expressed. We have seen that velocity can be expressed as 1 by root under mu and epsilon. And we have c as the velocity of light in free space or vacuum as root under mu naught and this as epsilon naught. So if you use both these equations, you will get that we can express v is equals to c by root under mu r and epsilon r. And since this is a lossless dielectric medium, so we assume um, mu r to be equal to 1. So we have v equals c by root under epsilon r, and then rearranging it, we'll get epsilon r equals c by vp whole square. So substituting the value of velocity of light in free space and the phase velocity that we already calculated over here, solving it, we get the relative permittivity of the media as 4. Now all that is left is the wave impedance. The wave impedance eta can be given by eta naught divided by epsilon r. So this you can get this formula by you already know this, that eta is equals to root under mu by epsilon. Yeah. So and now you know this, and you have this. So you can express it as root under mu naught mu r and epsilon naught epsilon r. Yeah, pardon me for this terrible writing. So so you just separate this as you can, and you can write this as a separate root. So you will have mu naught by epsilon naught as eta naught, and mu r is 1. So you will have 1 by epsilon r. So you can write this, hence you get this expression eta is equals to eta naught by root under epsilon r. Substituting the value of epsilon r from what you've calculated over here, and as I said, this we know the wave impedance for free space, which is 377. So we get this particular answer. So that's all. This pretty simple example also helps you recollect all that we have covered in the last few slides. So I'll stop over here. Take any questions that you might have. I see we have 5 responses. Quite a few people, I think, missed the poll as well. But anyways, any questions that you might have till now? Next, we'll discuss the questions from the assignment and then in the class. Okay, I think this was pretty straightforward. Yeah, so this was the assignment that we had that we got in the last week. So the first question was to derive the point form of Maxwell's equations from the integral form, and we have the hints that you have to use the Gauss's divergence and Stokes' theorem. So solution for this is available in this particular website. Since this is pretty straightforward and a standard textbook exercise, you can refer to the website, and maybe if you have any doubts, we can discuss on it. But I don't think it will be that complex for you guys. The second question was to derive the continuity theorem. So we'll discuss this in the next slide. The question 3 was what are the source quantities in Maxwell's equations? So yeah, anybody wants to volunteer to help me figure out which are the source quantities? Maybe someone. Okay, maybe not. So yeah, so this charge quantity over here, this and these currents quantities over here are the source quantities in the Maxwell's equations. Now the fourth question was to derive the wave equations from the Maxwell's equation. So we again got this question today. Maybe we can discuss this in the next class. Again, write in terms of phasors the time harmonic Maxwell's equations for a simple medium. So we've already seen this in today's class, one of the slides. I think we can refer to this time harmonic slide which we saw. I'll share the slides at the end of this class. Now the sixth question is very interesting. What is the difference between phasor and a vector? I think I'd like to hear from you guys. So we'll not discuss this today. Leave it as an assignment just in case if you did not get time. We'll discuss this in the next class. Next. Yeah, coming to the second question, continuity theorem. So the continuity theorem essentially is relationship between the current density and the rate of change of charge. So taking the total charge in some volume, and so example, we have this particular volume and there is some charge inside, and these charges are moving out of the surface. So the So charge inside this particular volume can be expressed by as the volume integral of the charge density of this particular volume. So we take the we know the charge density, and if we take the volume integral, we'll get the total charge inside the particular volume. Now, if the charges are if the current is flowing out, that is, the charges are flowing out of the boundary or flowing inside the boundary, the local conservation charge says that this rate of change of charge with or the current is the surface integral of the current density flowing inside or out inwards or outwards of this particular surface. So this current is equal, again, this evaluates as current, and this also evaluates as current. So this is the rate of change of charge, and this is the surface integral of the current density moving in or out of the that particular surface. Now, if we use this particular equation one to rewrite the left side, that is, if we substitute this over here, so we have volume integral on the left hand side, and again we have by using the Gauss's divergence theorem, we can convert the surface integral to a volume integral. We'll have this both volume integrals, and if we bring both of them to the same side, and this equates to 0. So we can represent this particular if this integral is 0, we can write this as the 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 rate of change of charge, the time is equals to the negative gradient of the current density. So this is the continuity equation, the revision for the continuity equation. So your next assignment will be to derive this continuity equation from the Maxwell's equation. So I'll include this in the coming assignment. Yeah. So that's all for today. If we can pause over here and take any questions that you might have related to the assignment or this derivation. So yeah, so we have this assignment over here. Any questions from this assignment or derivation? So yeah, so maybe not. Anyways, you are free to reach out to me on mail or WhatsApp, so we can take any questions there as well. So we just discussed this derivation, and your next assignment is to derive the same equation using the Maxwell's equations. Today we covered the Maxwell's equations, the time harmonic fields, the boundary conditions, and wave equations. So we'll start with again the wave equations in the next class. Do a quick review of today's lecture and look at uh, lossless, lossy and lossless conditions for the wave propagation, and we will discuss on energy and power of the wave. So yeah, so in the next class will be again continuing with the electromagnetic theory, which is the module 2 for this course. Yeah, so that's it for today. Any questions you might have regarding class logistics or anything that we discussed today, you can ask now, or in the WhatsApp group if you whichever is more comfortable to you. So that's all we had to cover for today. Is you I can take questions now, or yeah, thank you. Maybe we'll stop the recording here. Okay, so if there is no questions, then I'll stop the recording. So no questions.